Hello everyone, welcome back to the channel. I'm Nehemiah. In this video, I'm going to teach you all the system design fundamentals that I know. System design is the process of defining the components, the architecture, the modules, the interfaces, and the data flow of a system. It involves understanding networking concepts, architecture patterns, web concepts, scalability, performance, storage, security. I am going to make sure I teach you how popular platforms in the world are designed. I can't wait to get into the next section where we're going to talk about networking concepts. See you over there. Hey everyone, in this section, I will make sure you understand IP addresses. Today in our world, we communicate using several devices. For example, one can be a phone, and another can be your desktop or even your laptop. For the laptop to communicate with the phone, or for the phone to be able to access a website, or the laptop be able to access a website, you need a network. There has to be communication. For communication to happen between devices on the internet, they need to be uniquely identified. That unique identifier is called an IP address. An IP address is simply a numerical unique identifier for a device on the internet. For example, your phone can be uniquely identified as 10.0.0.1, and the laptop can be identified as 10.0.0.2. And these are called IP version 4 addresses. They are identified by 32 bits. And I'm going to explain to you how we come to the 32 bits. So the first number under the hood is represented by 8 bits. So 8 bits meaning 8 zeros and ones. It can be only zeros, only ones, or a mix of the two. Then the next number is also represented by 8 bits, which are simply 8 zeros and ones. The next one also 8 zeros and ones. The next one also 8 zeros and ones. The number 10 is simply the zeros and ones in base 10, which is the number we usually read from day to day. So when you multiply these 8s, okay, they are 4 8s. So 8 multiplied by 4, or 8 4 times, gives us the 32 bits. And the total addresses we have for IP version 4 addresses in the world are about, I think, 4.3 billion, if I'm not mistaken. But these addresses are getting exhausted, or they are not enough. Probably by now, they're not enough. I should have checked before recording this video whether they have been exhausted or about to be exhausted. But the point is that they are not enough. And because of that, a new address system was introduced called the IP version 6. Okay, it has more address space and even better security. IP version 6 is a 128-bit system. Okay, and the way it's organized is that the numbers are represented in groups of hexadecimals. So hexadecimal, I'll maybe write that word. I'll say hexa, if I can remember the spelling, hexadecimal. So hexadecimal simply refers to numbers from the range of 0 to 9, and then I think A to F, if I'm not mistaken. Okay, but the total should be 16 of them. So the addresses in hexadecimal, if you look at them, they are separated by full colons. For example, you can have a 1, 3, 4, then maybe a full colon, then you have 1, 3, B, 2, full colon, okay? And it goes on and on a number of times. But how many times? Only 8 times. So you have 16 bits instead of 8, you have another 16 bits, okay? And if you multiply 16 bits 8 times, you should get 128. If I'm wrong, please, I failed math in high school. Correct me in the comment section. But that's how you get to the 128 bits for IP version 6. So IP version 6 gives us more address space. Now, I want to talk about something important about private IPs and public IPs. It's a very important concept I need to put across to explain the concept of the NAT, and you'll understand what NAT is in a minute. So assuming the whole internet, okay, you can consider it to be public. It's actually public, okay? The whole internet is public. And then you have your home, okay? Assuming this is your home network. In your home network, you have a phone, so P for phone. You have a laptop, so L for laptop. And you have a desktop, D, okay? All of them need access to the public or the internet. You can decide to have your phone having a private IP address, meaning it can only be accessed in your home network. For example, it can be maybe 10.1.1 point maybe 2. Then for the laptop, 10 means a different color for this. 10.1.1.3. Then for the desktop, 10.1.1.4. But these are internal addresses and they are private to the home network. Once you want to access them to the public, you can use what we call the NAT. NAT in full is network address translation, and it's used to map private IPs to the public. Okay, so for example, since we have only private IPs in our home network, we can have NAT giving us an address like 10, that means something else like maybe 192.1.1.1, and this becomes our public IP that we use to access the internet. Okay, so NAT is very useful. It helps us, number one, to have security by protecting our internal devices. And also it helps us to preserve IP version 4 addresses. Like I told you, they are limited. Okay, because imagine if all devices had public IPs, then it wouldn't be enough. So NAT helps us to have conservation of IP version 4 addresses, but also provides security, okay, by protecting our devices from the internet. So every device, okay, will communicate to the outside world, to the public, okay, using this address. And that is the power of the network address translation, simply used to map our internal IP addresses to a routable public IP address. In the next section, we're going to talk about DNS, and we shall understand IPs even at a much deeper level. See you soon. In this section, we shall understand how DNS works. If you're enjoying this video so far, please hit that like button, share and subscribe. Let's talk about DNS. DNS is very, very important in system design, and there's no way we can talk about system design and understand networking and communication without it. DNS is known as the phone book of the internet, and let me explain why. First of all, you have to understand what DNS is. DNS is an abbreviation. So it's an abbreviation for domain name system. So the N, if I can type very, very fast, is domain for D, N for name, and S for system, domain name system. It is referred to by many as the phone book of the internet. Why? Because imagine if you have a phone, okay? Not imagine, but I assume everybody, of course, has a phone, probably at this time. And you have to memorize all phone numbers in your phone. That is quite a work. The easiest thing to do would be to associate a name to your phone number. For example, Nehemiah, instead of knowing 077510, okay, you simply know the name. And it makes it easier for you to look up and call someone. In the same way, instead of us memorizing IP addresses, the internet has hundreds of domain names and also hundreds of IP addresses. Imagine having to memorize a number like 192.0.2.1, and then you have to do this for every website. It is quite a work. And note that these are phone numbers. So for every website, you may have to memorize several numbers. If you know about 10 websites, you may need to cram or memorize 40 numbers at least. Okay. But instead of that, for example, if I wanted to find out Google's homepage, I simply type google.com, and google.com is translated to 192.0.2.1. Do you see how easy this is? So google.com becomes the domain name, and 192.0 and 2 and 1 become the IP address. So the domain name system is responsible for translating a domain name to an IP address. As simple as that. Now we're going to go a little bit deeper in how the whole thing works. But for this to work, we need to understand domain name servers. And I'm going to talk about them right now. So I'll copy a text box, probably this other one up here, and replicate it to use it to explain to you. So I'm going to talk about domain name servers, and probably need to use a different color. So for domain name servers, we have one server that is the first server to be interacted with in the domain name world. That server is called the root level. Let me just copy this. It's called the root. Need a different color. Root domain server. As simple as that. Root domain server. And it is the first server that you interact with in the domain name process. And I'm going to explain to you how all these servers come about. So this root domain server is responsible for sending or redirecting requests to another server, okay, called a TLD server, okay. But the root domain server looks at your domain, okay. For example, in our case, it's google.com, and it says, okay, this domain ends with google.com, or it ends with .org, or it ends with, let's say, maybe .io, and it sends it to an appropriate TLD server. So what is a TLD server? A TLD server is a server which is responsible for handling the top level domain. The last part of your domain, like .com, .org, .io, are called the top level domain. So let me rename this, just a minute, to TLD. So T for top, L for level, D for domain. So TLD server. Let's call it TLD server, like that. And like I've said, the root domain server sends okay, or redirects the request to the appropriate TLD server. So if it's .com, the request will go to an appropriate TLD server for .com. If it is .org, the root domain server will redirect the request to an appropriate .org TLD server. If the domain ends with .io, the root domain server will redirect the request to a TLD server that handles IO. Okay, I hope you understand that very well. Actually, before we go ahead, the best way to name this is, for example, for the first one, I need to call it root DNS server, okay, or simply servers, okay, because there's more than one in the real world. Then here we have TLD domain DNS servers, okay, just to make it clear in your mind that we have more than one. So just come on. I was trying to select the box, but it can't pick it out. But that's okay. So I hope now you understand that we have the root DNS servers, which are responsible for understanding your domain name. Okay. And when that domain name is identified as a .com or a .org or .io, the request is redirected to the appropriate TLD server, because there's a TLD server that handles .com, one that handles .org, and one that handles .io, and the other extensions. After that, we have another server. I'll copy this and paste. It is called an authoritative DNS server. Now, when the TLD server has got its request, its responsibility is now to redirect that request to the appropriate authoritative DNS server. That DNS server is the one which understands and stores the actual mapping of the domain name to the IP. For example, in the example I gave right up here, if you can quickly copy and paste it. If DNS was trying to look up google.com, then the authoritative name server will be responsible for returning this value 192.0.2.1. As simple as that. So the authoritative server is the one that actually stores the IP address. Then there's one more that I want to talk about. If I can copy this accurately and then drag it down, it's called the DNS resolver. These ones sit at the ISP level, and they are responsible for caching. Very soon we're going to talk about caching, but think about caching as a way of storing something, okay, temporarily. So these ones sit at ISP level. So what is an ISP? An ISP is an abbreviation for Internet Service Provider, simply the company or organization that gives you internet. For example, in my country, we have things like MTN, things like Airtel, and so many others. Maybe it could be Starlink for you. It could be any. Also, these are responsible in handling DNS to an extent, and they accept queries from the user and return the appropriate IP address in the event that it was cached on it. And you're going to understand the role of DNS resolvers in a minute. So now that I have talked about what domain name servers are and what they do and what some examples of these servers are, like I've told you about the root domain server, the TLD domain name server, the authoritative DNS server, and the DNS resolver. Let's now go to the actual process of how the whole thing works. So I can copy my title from here to save space and drag it down, not to save space, but to save time rather, which is not that much. So you can say how it fits together. Okay, so assuming we are now in our browser and this little box represents a browser that a user is going to use to search for a particular domain. Okay, so a user is responsible for typing. Maybe they type, they say, give me example.com. Could be anything. Example.com. If I quite not use my company that I've been working on recently. So I need to copy this text. So I'll paste it down here and I'll say arrow bound ventures.com. Then I'll reduce this slightly. Okay. So if a user types this in their browser, the first thing is that the browser cache is checked. Okay. The browser cache is checked to see if that domain has been stored temporarily in the browser cache. Think of cache as temporary memory. So the first time, it will not be found in the browser cache. So what happens is that a check will be done on the OS level. Okay. So OS stands for operating system. So if it is Windows, it will check in the Windows cache. If it is Mac OS, it will check in the Mac OS cache. If it is something like Linux, it will be in your Linux cache. So again, the OS cache is looked up into to find out the IP address for airboundventures.com. If it's not found, the next step is to move to the authoritative name server. Okay. So I want to create nice visual arrow. So next step is the authoritative. I'll just say A for authoritative DNS server, just to save time. Okay. And I've told you this. Wow, this is wrong. Okay. And I'm sure many of you are already screaming, man, what are you doing? So I'll delete this. It's not the authoritative name server, but the DNS resolver. And I've told you that these are used by ISPs to catch requests. Okay. So for the first time, the DNS resolver will not have the IP. And then we shall have a request now being sent to the root DNS server. So I'll say R for root DNS server. Root DNS server checks and says, is this a .com, a .org, .io, what's up? Then it sends it, in our case it's a .com, it sends it to a .com TLD server. TLD server. Then this .com TLD server redirects the request to a server which is the authoritative name server. Okay. I think earlier was probably high or something. Why was I putting this server right here in the place of the resolver? So authoritative DNS server. And it will be responsible for returning the IP address. Okay. As simple as that. And then in this case, you'll find that the DNS resolver will now catch this IP address. The OS will also catch, and the browser can also catch the IP address. So that the next time we make a request to airboundventures.com, the browser simply returns the IP immediately. If you clear your browser, it can be got from the OS. If your OS is probably cleared, it can be got from the DNS resolver. Otherwise, we go to the root and so on and so forth. I can talk about some types of DNS records. So I'll create a title, and this title will be called DNS records. I'll talk about the most popular two that I'm sure most of you will definitely work with. The first one is called an A record. Okay, an A record. So an A record points a domain to an IP address. Domain to an IP address. Like in this example, it can point airboundventures.com, okay, to an IP address. I want to write this better. So this is a domain to an IP. So airboundventures.com can be mapped to 192.1.1.2. And again, this record is stored in the authoritative DNS server. Then another one is called the CNAME. So the CNAME record maps a domain. It maps a domain to another domain. An example could be mapping Airbound Ventures, probably www.airboundventures.com to, I'll drag this just below here, to that. Okay. So www.airboundventures.com to airboundventures.com. The difference is that the CNAME is slightly slower than the A record because it has to resolve twice. Okay. So www.airboundventures.com resolves to airboundventures.com, then airboundventures.com resolves finally to the actual IP address. So DNS is very important and helps in systems that actually should probably never go down. Okay. And you find that loads or requests are balanced and spread across several DNS servers. And that helps with an important thing in system design called scalability that we are going to talk about very soon. Because when requests are too many, for example, for maybe Google.com or YouTube, you don't want all the requests being handled by only one DNS server. So all requests are sent to several DNS servers, not only one. So I hope you've picked something from this. See you in the next section where we're going to talk about the client server model. Hey everyone, welcome to this section. We have talked about IP address, we talked about how DNS works, and now I want us to look at client server model. In the real world today, we have what we call clients. A client can be typically any device on the internet that makes requests. This could be something like your mobile app, or it could be your browser on your laptop, or your desktop, or your tab, or it could be a dashboard in your car. It could be probably something like another API. Anything on the internet that makes a request can be a client. Just have that in your mind. Clients are responsible for making requests. And these clients all have a unique identifier on the internet. So your mobile device has an IP address, the browser has an IP address, everything has to be uniquely identified. And these clients are responsible for sending requests to a particular server. The server must also be known. This server can be responsible for serving to you a web application. So I can call it a web server, or it can be an application server, or you can have, for example, a database server, which is responsible for responding to queries to a database. Or you can have an email server, for example, responsible for processing SMTP stuff, like maybe your Gmail server, it could be Yahoo or whatever you use. The main point here is that clients send requests and servers return with a response. In the world of the web, clients typically send what is called an HTTP request. HTTP request. And HTTP is simply an abbreviation for Hypertext Protocol, which is simply a set of rules or principles that clients and servers on the internet use to communicate on the web. As simple as that. A set of principles, protocols, or rules that clients and servers use to communicate. So there's a standard that when a client wants to communicate to the server on the internet, it has to send what is called an HTTP request. And we shall go deep into this soon. Then, in the same way, a web server must respond with an HTTP response. These have particular formats that we're going to look at when we go deeper into system design. Okay? Now, sometimes when a client makes this text is supposed to be HTTP response and not request. Sometimes when you're speaking and you're writing, your mind can subconsciously do other things. That is why they say it's best sometimes to focus on one thing. All right, sorry about that. Let's continue. I was saying sometimes when a client sends a request to a server, it can wait for that request. Okay, so let's say we have another client over this side sending a request to a server. So I'll say S for server, and this side I'll say C for client. When a client sends a request to a server, it may have to wait for a server to give back a response. This is called synchronous communication. Okay, this is a term that you need to understand. Okay, synchronous. Can I spell this correctly? Synchronous communication is a type of communication whereby when a client sends a request to a server, they must wait for the response. I'm sure many of you have interacted with many web applications. For example, when you submit a form, many forms on the internet, you cannot do anything else on that web page until you have got a response from your form submission. And of course, like I've mentioned in the previous section, all this happens on a network. You can't have the client server model without a network. All these HTTP requests and HTTP responses happen over a network. That is why I stressed in the previous sections talking about IP addresses and how DNS works. In the HTTP request response cycle, still the DNS process happens. Have that at the back of your mind, because I won't go through how DNS works when talking about the client server model. But know that under the hood, everything goes on in milliseconds. All right. So the other type of communication can be that when a client sends a request to a server, the client can go ahead to do other things. Okay. And the server can respond at any other time. Maybe you send a message, for example, on WhatsApp or any other messaging platform. You send a hi to your friend, and that hi can reach the receiver maybe after 2 minutes, 5 minutes, 4 minutes. And even then, they can reply to you immediately, and you can receive the message immediately, or after a minute, or after an hour. It does not matter. But the whole concept is that a client sends a request to a server, and they don't have to wait for the response. The response can be returned back at any time. In other words, it is non-blocking. Okay. This technique or this way of communication is called asynchronous communication in the client server model. So it is asynchronous communication, and it's called a non-blocking communication mechanism, meaning clients are not blocked or stopped or prevented from doing any other activity in the application. They can make requests for something else. Then the opposite is synchronous communication, whereby the client is blocked or prevented from doing something else until the server responds back with a response. Understand this and it will help you. An example of synchronous communication can be like I've told you when you're submitting your form, like a login form or another form on the internet. Many forms have a synchronous way of behavior. Then an example of asynchronous communication I've given you is like when you're going to maybe chat, okay, with your friend, when you're going to do things like WebSocket connections. Right now, you don't know about WebSockets, but we shall talk about them soon. When, for example, you're receiving a notification, in some systems, you don't have to receive a notification immediately. When, for example, you purchase a good on an e-commerce website, you've bought your nice gadget, tech gadget, you can receive a notification after like maybe 2 minutes by email or an in-app notification. That is asynchronous communication. Many times these notifications are not sent immediately. In other words, a user receiving a notification should not prevent them from doing other things. Okay, you can buy something and go and look at maybe other products, and in the background, the server handles everything and can notify you when things are ready to be processed for you. So understand this concept and it will help you. Many times you're going to decide whether you need to have synchronous operations or asynchronous operations. All right. The next concept I want to talk about in the client server model is stateless versus stateful. And you're going to understand that soon. Again, I'll have here my C for client. I want to use a different color. And then I have my S for the server. When you're talking about communication in the world of web, a number of things can happen when you're sending a request to a server from a client. Sometimes it can be mandatory that a client has to send information pertaining to their request, all information concerning a request. Sometimes a client does not need to do that because the server understands and remembers it. What am I driving to? I'm driving to two technical terms. One term is called stateless. I want to copy this and write it here. I'll say statelessness. Okay. I'll say stateless request. And then I'll also put one down here called stateful. Okay. And maybe just change the color so that you can see it better. I think this will do. So a stateless request and a stateful request. Think about state. I want to talk about state first of all. State is simply data, okay, being kept. Okay. State is simply data or memory. So when I say a client sent a stateless request, it simply means that the server has no memory of that request. The server does not know any request. It treats every request uniquely and separately from other requests, which means you who is designing this application must make sure that every request contains, a client has to make sure that every request contains all the data that is required for that request to be executed. Otherwise, the server has no memory of what you're doing. Okay, it doesn't remember any previous request, it doesn't remember any previous 2 or 10 or 5 requests. So every client request must contain all the information required for that request to be successful. Why? Because the server does not store any state for that request or for any other request. Then the difference is that stateful requests, I've seen a spelling mistake. Let me remove this. Stateful. Okay. The opposite, which is stateful request, means that the server has memory of the previous request. Okay. In other words, the server stores what is called a session. And soon I'm going to talk about sessions. If I forget, don't hesitate to remind me. Like I told you, this is an introduction to system design, and I'm laying up a foundation that is going to help you understand so many deep concepts. By the time I start designing real world applications, it should be easy for you to understand everything because you've understood all the foundations. So let's get back to this. Stateful requests simply mean that the server remembers what the previous request might have had. Okay. And this is achieved using things like user sessions and cookies. Simply, the server has memory and keeps track of client requests. This can be actually very, very good for things like maybe banking applications where you need to remember all the user state, okay, when they logged in, what did they do, for how long have they been logged in, that kind of stuff. It is very important. Situations where you don't need maybe to take care of things like state and you want it to be stateless could be maybe in a very quick gaming world. Okay, you may not need to remember the requests in real time as people are gaming online. Okay, I hope that makes sense. Okay, some people actually do a combination of both. So I want you to have in your mind that you're going to design systems depending on a need. You may find in one module in a system, you need a stateless request. Somewhere else, you don't need a stateless request. It must be stateful. Sometimes you may need a mix of the two. Some applications don't need stateful, but need stateless. Okay. Others need synchronous communication. Others need asynchronous communication. Sometimes you may need to combine both. It depends on the use case. Always think about the need first of all before designing a system. That is the goal of me explaining to you these fundamentals. So thank you for understanding this. I hope you have. If you haven't understood, please leave a comment in the description. And of course, I will see you in the next section. Hello everyone. After understanding the client server model, the next thing I want you to understand is proxies. When you have a client and server, you can have an intermediary. So like, I like drawing. So I'm going to draw a client. So this little box represents a client. And then on the other end, we shall have a server. And like we learned in the previous section, clients simply send requests to the server and the server responds with a response. You can set up an intermediary in between here. This intermediary is called a proxy. A proxy intercepts the request from the client to the server. And there are basically two types of proxies I'm going to share with you. The first one is called a forward proxy. To explain a forward proxy, I'll create another simple box here representing a client. on the network. And this client, like we know, sends a number of requests. But this time, we set up an intermediary that will be responsible for hiding the IP address. If the client has an IP address like 192.0.1.2, this intermediary can hide this IP address by a strategy called masking or IP masking. And it shows a different IP, which is not the original IP. By doing this, it helps you to be anonymous on a network, but also provides a way of preventing attackers from directly attacking you. This intermediary is called a forward proxy. So a forward proxy is a type of proxy that intercepts requests from a client, or it is simply a proxy that sits in front of a client. And like you've seen in this diagram, a proxy helps you to also catch. Catch is very good thing that we get from a forward proxy. When a client has things that they request for very, very often, the forward proxy can catch and hold the responses for frequently requested things and serve the responses to the client immediately. This forward proxy can be also used for several other things like content filtering. Maybe you want to prevent clients from malicious websites. The key thing to remember is that a forward proxy sits in front of a client. Then we talked about a server being able to receive requests from the client and return a response. A server can also have an intermediary sitting in front of it. And this intermediary intercepts all incoming requests. And this intermediary is called a reverse proxy. Reverse proxies sit in front of servers and give certain benefits. One of them is SSL termination. And this simply means that when a request comes, and this request is an HTTPS, okay, the S stands for secure, meaning that the request has been encrypted. SSL termination simply decrypts that request and forwards it to the normal HTTP server. So instead of having SSL termination on the server, we can offload that work to the reverse proxy. Reverse proxies help us with also balancing the load. In the next section, we're going to look at load balancing. And with load balancing, it simply means that a reverse proxy can help us to distribute traffic to several servers so that a server is not overwhelmed. Also, reverse proxies can be used for simple caching and also security by adding a layer of protection to your server. The key takeaway should be that forward proxies sit in front of clients and reverse proxies sit in front of servers. An example of a forward proxy could be the common VPNs that you use. And an example of a reverse proxy could be tools like Nginx. So right down here, tools like Nginx. Have I spelled it correctly? You have the AWS load balancer. We have tools like Cloudflare. In the next section, we're going to get even into another concept. Again, make sure you understand everything I'm talking about because I'm going to combine them when dealing with case studies in the real world and designing real world systems. See you in the next section. In this section, I'm going to introduce load balancing. It's a topic we're going to talk about a lot when studying how popular web applications have been designed. So I thought it wise to introduce it early as a fundamental concept. When talking about the client server model, we talked about clients sending requests and servers dealing with those requests and returning appropriate responses. And a client or clients can send a number of requests to the server. What happens if a server receives too many requests that it cannot handle them anymore? For example, let's say we have a server that can handle a maximum of 10 requests, but then you have many clients that are sending requests, and these requests probably reach 30 requests. Again, this is just an example. In the modern day, a server can handle more than 10 requests, but to be maybe more realistic, I'll say a server can handle probably about 1,000 requests per minute. But then, for some reason, your application becomes so popular that you start getting over 30 million requests per minute. Your server will obviously be overwhelmed and it will crash. This creates a bad user experience, not only for you as the developer, but for your users, and you can lose a lot of business. One solution is to distribute the load. We can say server A handles 1 million requests. We create a more capable server. So server A can handle 1 million requests. Then we have another server probably that can handle a similar number of requests. Then we have another server, server C, that can handle a number of requests. And then we have another server D handling a number of requests. These requests need to be distributed to these servers. Right now we have 1, 2, 3, 4 servers. A tool that can help us to do this is called a load balancer. So I'll draw a simple box here and label it LB as an abbreviation for load balancer. So when clients this time send requests, the requests will go through our load balancer, and the load balancer will be responsible for distributing the requests to our server so that the servers don't get overwhelmed by the 30 million requests. I've only put here 4 servers, but in the real world, you'll find that you can have hundreds, thousands of servers that are handling millions of requests for your application. So this is where a load balancer helps us. Number one, it helps us to avoid overwhelming a single server. It also helps us to avoid failure in case, for example, for some reason, server B crashes. Okay. The users should continue, or clients should continue getting access to what they need. And a load balancer can help to know that, okay, server B is down. Let me send a request to either server A, server C, and server D. That's what load balancing is all about. It's about distributing traffic evenly across servers so that we don't have any downtime. Okay, so this is very good and something that you need to understand. I need to talk about types of load balancers. And when talking about types, you can categorize them according to one, the layer you're dealing with. So the layer, or you can categorize them according to the deployment strategy. And I'll explain what I mean by these two. So to talk about the layer, in networking, there's something called the OSI model. If I can quickly go it, the OSI model. OSI model is a conceptual system. Okay, let me write it here. OSI. So the O is for open, the S is for systems, I is for interconnection. So open systems interconnection. It's a conceptual model which simply explains 7 layers, okay, in the networking world. And these 7 layers simply explain how data moves on a network. They are 7 layers, like I've said, but right now when talking about load balancing, I'm going to mention 2 layers. One layer is called layer 4. Another one is called layer 7. So there are 7 layers, layer 1, 2, 3, 4, 5, 6, 7. When talking about load balancing, this is what they call layer 4 load balancing, and is what is called layer 7 load balancing. With layer 4 load balancing, traffic is distributed based on network data like the IP address and port numbers. Then, for layer 7 load balancing, traffic is routed based on the request content. Have that in your mind. Layer 7 traffic is distributed based on the request content, like the body, like the headers, and of course, very soon we're going to talk about protocols. And the protocols that are dealt with in layer 7 are HTTP. I touched on this slightly in the previous section, but we're going to talk about HTTP again with more details. And then for layer 4, we have protocols like TCP and UDP. Okay, TCP and UDP. For now, you don't have to understand them right now, but we shall talk about them in the next video at a much deeper level. So that's what you need to know for now. That when you're load balancing, you can load balance at the layer 7 of the OSI model or at layer 4 of the OSI model. Again, OSI model is simply a conceptual framework that lays out a number of 7 layers, simply telling us how data moves through a network. As simple as that. And you can load balance at layer 7 when you actually are interested in the request content, or at layer 4 when you're interested in basic load balancing, but you want load balance based on network data like port numbers and IP addresses. Next up is the deployment way in which you can load balance. What do I mean by this? I mean there are several ways you can set up your load balancer. You can have a load balancer which is a hardware device, okay? Or you can have a load balancer which is software based, like Nginx, Proxy, okay? I think for hardware there is one called F5, if I'm not mistaken. There's a hardware load balancer called F5. For software, you have things like Nginx and Proxy. Then you can have cloud-based load balancing. Cloud-based, for example, the AWS load balancer. Now, I want to talk about load balancing strategies. How do you load balance, whether using hardware or software on the layer 7 or layer 4? So I'll say strategies of load balancing. Once you understand the concept, applying the things becomes very easy. So when you want to load balance, the number of strategies that you can apply. One of them is called round robin. And I'm going to explain each strategy step by step. So the round robin strategy works like so. Imagine you had servers. You have server A, then you have server B. Okay, you have another server here, C. And then you have requests coming from a client. Let me create another server, maybe a server F. Round robin works in such a way that requests go in circular order. The first request will go to client C, not client C, but server C, then server A, then server B, then server F. Once the last server is reached, we repeat. We go back to server C, then to A, then to B, and then to F. That is how the round robin strategy works. We have another one called IP hash. IP hashing. So how does IP hashing work? When you have your servers, okay, each server has an IP address. So server A having an IP like 192.0.1.1. Okay. Server B also has its IP address, maybe 192.0.1.2. And again, you have another server C 192.0.1.3. And then you have your client C trying to make requests, okay, through your load balancer. And of course, your load balancer should distribute traffic to these servers. So what can happen is this. You can find that your IPs, okay, are hashed. Okay, so you have a hash for this, some random string hash. You have a hash for this. You have a hash for this. So what happens is that these IP addresses are given to what is called a hash function. And this hash function should always produce the same hash for the IP every time. As simple as that. So that, for example, if a client C, okay, has always got its responses from server A, that should always be maintained. You can have that kind of strategy that clients get responses according to the IP hash of the server. And you can have, for example, let's say you have another client here, or client tagged with B, okay? Another client decide that client C and B will always get responses from this, okay? And then this other one gets from this. But the whole idea is that IP hashing is used to ensure that clients get consistent processing of their requests from a particular load balancer. Not load balancer, but a particular server. And what happens is that the IP of the server is hashed by being passed through a hashing function. Then we have another strategy that will be called list connections. So we have the list connections. And you might actually guess what this does before even I explain it. Now, list connections, assuming again we have our servers, okay? We have a server A, we have a server B, and we have a server C. Each of them is processing number of requests. But probably server A has only 2 requests for now. Okay. And server B has 3 connections. Okay. It's now processing. And server C has 1. When a new request comes, okay, a new request comes from a client, what happens? Think about it. If it's called list connections, what happens when we get a new request from a user or from a client? The server with the list connections, in this case, which is server C, will be given the opportunity to process that request. So now at this point, it now has 2 requests. Okay. The next time another request can come, it's given to server A or server C. Any of them can process because they both have equal number of requests. Let's say we take server A or even server C still. Okay. Now it has 3 connections. Assuming maybe these connections take sometimes longer than expected, maybe about a minute. And requests are coming so fast. Okay. Maybe every second. The next time a request is made, we look for a server with the list connections, which will be server A. So the request goes to server A. So we have 3 connections. So it keeps repeating this again and again. Okay. And one thing I forgot to tell you is that strategies of load balancing can be categorized according to either being static or being dynamic. So IP hashing and round robin are called static. Okay. Static load balancing strategies. And then list connections and the others I'm going to share with you are what is called dynamic strategies. Okay. So what I'm going to talk about here are called dynamic load balancing strategies. Why dynamic? Because the things that you use to decide the load balancing or the traffic distribution are always changing, because the server with the least connections can change at any time. One which had the least connections at one point can have the most connections at any other time. Then I want to talk about another strategy, which is also a dynamic load balancing strategy, and it's called the least response time. Least response time. So if you have about 3 servers, like I drew above, I'll just do them again. So we have our 3 servers, A, B, and C. Server A takes probably about 10 milliseconds to respond. Server B takes about maybe 20 milliseconds to respond. Server C takes 3 milliseconds to process a request and produce an HTTP response. What happens is that when a new request comes, we have a new request from a client, the load balancer will determine who should receive and process this request by looking at who responds the fastest when a request has been given to them. And in this case, it will go to server C. Okay. So as I explain these things, you should now be thinking about the disadvantages of some of the things. Because imagine if server C responds in 3 milliseconds. What happens if you have 1 million requests? Don't you think you might have only server C receiving those 1 million requests because it responds fastest? Then what if it receives all the 1 million requests because it responds fastest, but it crashes because it can only process 500,000 requests at a go? I think you start seeing some disadvantages of these strategies. That is why in the modern world, we have better strategies or hybrid mechanisms. Then another strategy that is a little bit better would be called the adaptive strategy. So adaptive works in such a way that the load balancer continuously monitors the state, okay, of the servers and decides who should get traffic depending on maybe things like maybe the CPU usage, maybe the memory usage, probably the request types, the number of requests, the response time, okay? So the load balancer constantly monitors the servers and adapts, okay, changes its strategy depending on what is going on depending on what the need is at a particular time. Then we have another one called the weighted load balancing. So with weighted, the servers are given particular weights according to their capacity. So a server which has better capacity is given a higher weight, maybe like a weight of 10. Another one, maybe server B is given a weight of 5, and another one is given maybe a weight of, for example, maybe 13. So depending on the capacity of a particular server, we give particular weights to these servers. And a weight simply tells us the power or capacity of that server. And we give requests or we distribute requests to these servers depending on their capacity or depending on their weights. Now, this is just basic load balancing, but there are more advanced load balancing strategies like, for example, weighted round robin load balancing. And let's move on to the next section to get deeper into the fundamentals of system design. Again, like, share, and subscribe. If you have any question, please leave it in the comment section. Hey everyone. In this section, we shall discuss API gateways. Let's say you have a number of clients. So one client here is an Internet of Things application. Another client here is probably a browser running on your laptop. Another client is your mobile device. And all these need help or need to send requests to your backend. So you have your backend server here. And this backend server, like we know in the client server model, is responsible for processing every request and returning the appropriate response. So the IoT devices can send any number of requests. The laptop can send directly to the server. The mobile can't send. So you see a problem, we have a direct access to our server, which is something that an attacker can be very happy about. To solve this, we can use an API gateway, which is a centralized tool. An API gateway, which simply acts as a reverse proxy to sit in front of our server. And this will be a centralized tool where our requests first go to before reaching the server. So the IoT devices send their requests to the API gateway. The laptop also sends to the API gateway. The mobile devices also sends to the API gateway first. Then this central point called the API gateway is now responsible for routing those requests to the appropriate server. Now, that should give you a hint of load balancing. And that is one of the benefits API gateways can come with. You can configure your API gateway to do load balancing, that every request is distributed to the appropriate server according to your load balancing strategy. I explained load balancing strategies in the previous section. So if you missed that, please check it. Then after that, we have another advantage that can come with working with an API gateway. And that advantage is security. Instead of having the IoT device authenticate separately, laptop separately, mobile device separately, with each of the server instances that you have running, the best way is to have a central place where you have security. And with security, I'm mainly talking about authentication and authorization. So authentication mainly deals with verifying who a client is, who a user is. And then authorization deals with identifying what this user can do. So we first authenticate a user or a client, then authorize them. The other advantage that an API gateway can give us is centralized logging. Okay, centralized logging and monitoring. We can find out what is going on in our application, find out the error messages, find out the bugs in one place. And this can help us with things like debugging, analytics, or you want to trace a particular request. All this is an advantage that API gateways give us. Sometimes the loggings can be used for things like auditing, to develop and produce audit reports. Another advantage that API gateways give us, and I think I've hinted on it already, is API composition and aggregation. Sometimes when you're building an application, you have so many API endpoints, okay? But you can have your API gateway consolidate all these endpoints into one single API call. Sometimes you might have a business request requiring you to process many API calls. But using an API gateway, you can harmonize all these many API calls into only one API call. So another thing maybe I forgot to mention is SSL termination. You can have SSL termination on your API gateway, which is an advantage to lift that weight away from your servers. We can also have things like bot protection, preventing distributed denial of service attacks, whereby in case someone wants to overload our server, they have to go through this API gateway, and this API gateway has a rate limiting, okay, configured. So you can have rate limiting, which is also a good security feature. We can have rate limiting in what is called throttling. So rate limiting simply restricts a user to access a particular resource per probably minute, per hour, okay? Basically understand that rate limiting is all about restricting a user or a client to access a particular resource in a particular window. So maybe you can say you can only access this particular resource 5 times in a minute. If you exceed 5 times, you have no access anymore. That is an example of rate limiting. A similar concept called throttling. Okay. So throttling simply refers to slowing down. So instead of stopping and restricting the access, you slow down. Okay. It's called throttling. You slow down the requests. So all these can be done in an API gateway. If you're an advanced user and you know something I've forgotten, please let me know. Something comes to mind, which is request transformation. Sometimes the servers expect a particular format of the request, but the clients have sent things differently. You can use the API gateway as a centralized place to transform every request before forwarding it or routing it to the appropriate server. So this is very, very important. And I hope you have understood what an API gateway can do. But a simple caveat can be not a caveat, but the best suit for this application of an API gateway could be when you're dealing with things like microservices and multi-client APIs, like I've showed you the IoT device, laptop, mobile app. Now, if you don't know what a microservice is, do not worry. This is something I'm going to talk about when I'm dealing with architecture patterns. I would avoid an API gateway if I had a very, very basic monolith app with minimal requests and responses. Okay. But in case I had high traffic among my microservices and multi-client APIs and apps, I would go for an API gateway for the benefits I have mentioned. See you in the next video where I'm going to talk about CDNs. Hey everyone, welcome to this section where I'm going to talk about CDNs. So, what is a CDN? A CDN or CDNs are a collection of globally distributed servers geographically. And like you know, I like demonstrating things using diagrams. So let's say we have a client. This client is going to request for a particular web page. Let's say a video, okay? Or web page or image. It could be anything. It could be static content. It could be dynamic content. And they make a request. Okay, for now, I'll not put load balancers or API gateways or any proxy. I'll keep it simple by saying they have access direct to an origin server. That has, I'll call this an origin server. And you're going to understand why I call it an origin server. But this server has the video, image, any kind of content that the client is requesting for. And this client is located in a geographical location. Maybe I'll say region A. This could be Africa, Asia, anywhere in the world. Region A. And this server is also located in region B. To get a response after a request has been made can take some time. And let's say because the distance, the geographical distance between region A and region B is too long or large, it takes probably about 10 milliseconds for the client to get a response. What if there was another server? Okay, maybe I'll say this is a server, and this server is, let me get another color, something that is visible to the eye. I hope this is visible. So this is another server, and this server is in a region that I'll call region C. All these are physical geographical regions. So region C, not B. And we decide to keep a copy of that static content or dynamic content. Let me go with static content. Let us say a video or image. So this time, this image that is being requested for is stored on this server in region C. And the time it takes to get a response, this time around, it takes about 2 milliseconds. Why? Because geographical locations matter a lot. And the shorter it is, the faster you have your response. So, how do CDNs help us? CDNs are simply servers which sit or are located geographically nearest or nearer to a client, so that clients get responses faster from the servers which are closer to them and not the servers which are far from them. Many times the origin server can be very far from you. And instead of making a request for data from the origin server, the request is given to you from the nearest server to you. This nearest server to you is called an edge server. Okay, edge server. I'll use the same color to write the word edge. So how does it work? For the first time, a client makes a request and the request is made to the origin server. The origin server returns a response back to the client. And that response for that static data, like an image or video or dynamic data, is stored in the edge server as a cache. Okay, remember I talked about cache in the previous section. Think about cache as a temporary storage of data in memory. So the next time the client asks for the image, we first check the edge server. If the edge server has it, then we immediately return a response to the client. If there's a cache miss, meaning we didn't get data in the edge server or what we want in the edge server, we make a request to the origin server. When we get data in an edge server, it's called a cache hit. When we don't have what we want in an edge server, it's called a cache miss. As simple as that. Now, there are so many things that edge servers give us, and I'm going to talk about them. But one thing I want to talk about is how these edge servers are organized. There is something called POP, which I'm going to explain in a minute. I need to clean up this board a little bit and go ahead to draw some more edge servers. So let us say region C has, okay, I'll leave this text, has a collection of edge servers. We have another edge server right here. I'll say ES for edge server. Could have another edge server here. We have another edge server here. And all these edge servers are put in kind of like an umbrella or collection. You may find another client in another place is being served by a different collection of edge servers. Okay, multiple edge servers helping a client from a different geographical region. Why? Because this collection of edge servers are geographically located nearer to that client. And these collections are called POPs. Okay, and POP is an abbreviation for point of presence. Point of presence. So do not get confused when someone talks about a point of presence. Simply refers to a collection of edge servers or CDNs which are geographically located nearest to the client. Then something else I can talk about is like the benefits. These CDNs help us to avoid overloading the origin server. In a way, we get load balancing. These CDNs also help us with SSL and TLS termination. These CDNs or edge servers also help us with things like rate limiting. Understand that and you'll be good to go. How do the edge servers and origin servers and these POPs manage everything? There's a concept or a setup that is called the routing, the request routing. Okay, request routing is a component of a CDN that helps with moving content from the origin server to the edge server to the client, as we've discussed. So if someone asks you what are the components of a CDN network, simply say we have the point of presence, we have the edge servers, we have the origin servers, and we have the request routing component. As simple as that. And maybe one more thing I can talk about is something called TTL. Okay, TTL. It's an abbreviation for time to live. Time to live. It simply is a configuration in your CDN settings that tells the server how long the catch should be revalidated or invalidated. In other words, if we catch an image, okay, let's say we're catching an image for about 1 hour, okay, after 1 hour, that image will be removed from the cache. As simple as that. Then something also called manual purging can be done. When you manual purge, you voluntarily remove cache. Okay, you don't care about the time to live. The time to live can be 1 hour, but in less than an hour, you can voluntarily manually remove that image from the cache. And of course, that means next time that image is requested for, a request will be made to the origin server. Then something else I want to talk about is called state, not state, but stale while revalidate. I think I should type all this. So simply copy and paste this down here. So the first thing I talked about is called the manual purge, where you voluntarily remove data from the cache. Then we have what is called the stale while revalidate. This simply means that the cache, which is stale, which is old, is served to the clients while under the hood, new, fresh, updated data is being prepared. As simple as that. Something else I want to talk about is compression. These CDNs help us to compress images and data, okay, so that we have lower bandwidth. Yeah, I was thinking about something I had forgotten, but yeah, compression is one of the good things we have with CDNs. I've also talked about rate limiting as an added advantage. And this, of course, helps us to avoid or survive DOS attacks or distributed denial of service attacks. Then what else comes to my mind? Have I forgotten? I think that's it. Well, I talked about SSL or TLS termination, and I'm looking at my book, which has my notes, to see if I've forgotten anything. I think that's it. So we've covered so many things, okay, in networking and communication. Next up, I'm going to introduce protocols. Again, I'm trying to make sure I cover all the system design fundamentals so that when I start discussing and showing you how you can design popular systems which are complex, you understand what is going on. Because I won't have time to go into the details of each of these concepts, but you'll see me talk about IP addresses, DNS, the client server model, proxies, load balancing, the API gateways, CDNs. And on top of that, I'm going to also be discussing several protocols and architecture patterns. So the next videos are going to cover protocols and architecture patterns. And then after that, we can go into things like scalability and going deep into these things. Okay, so I hope you've learned something big from this video. Like, share, subscribe, and in case of anything, please leave a comment. And I'll see you in the next video.